Just a reminder, I'm Simon Wansborough, board member of PHINZ and owner of Third Little Pig Construction. And today we do have with us Dennis from DCD Construction. Thank you very much, A, for being with us, Dennis, and B, for sponsoring these two webinar sessions. It's great to have you on board in the Passive House community. As we did last week, we've got the chat box open, so if you've got any questions, just chuck them in the chat box, and Dennis may answer those as he's doing his presentation, or he may leave them till the end. We'll just see how that goes. So Dennis is going to do a presentation loosely around lock-in effects, not just around foundation systems, but general things that we can avoid or make better in the houses that we build. And then after that, we're going to sort of open up to answer any questions that are remaining from that, but also a bit of just open discussion. The whole idea of these builders social sessions is just to share knowledge, to share information, so that we can all learn from each other how to do things better. So I will hand over to Dennis.
Thank you, Simon, for the introduction. That's much appreciated, and thank you for everyone who is here today. One of the things that I would appreciate is, while you're involved, if you feel so invested, please communicate early. If I don't see the message for whatever reason, Simon can interrupt me with a question, but it'd be good just to keep the dialogue going while we're going through. The idea of today is to share information with you in terms of my experiences to date, and to have a dialogue, an active dialogue around that, so that you ideally will leave with something more than what you came into this meeting with. I'll apologize in advance. The way that I've set up for today is a little bit awkward, so there'll be a toing and froing on the screen a bit. And if you bear with me on that, I'll start sharing with you. So my presentation is basically covers a fairly broad range of topics. I have sort of stuck with the generic idea that we're talking about the lock-in effect specifically around slab construction. I have gone a little bit fringe and also included what that might mean if you were looking at a renovation, what that could look like, and when you're there to do a renovation, the opportunities that you have as well in that space. The other thing that I will touch base on as well, ideally, is what I think becomes integral to a slab, certainly in this climate, which is underfloor heating. So as I said, I'll bounce around a little bit, so if you can just bear with me on that. It just gives you a bit of a background as to where I'm coming from and the climate that I work with here. So the lock-in effect, as I focused on for the purpose of today, is really based around the idea that once you proceed with an element of construction, there's very little opportunity to unwind that in the future. So a great example for that is often that if you go with double glazed windows today, unwinding double glazed windows for tomorrow is a very, very difficult task, and it's a major undertaking. It affects weather tightness, it affects interior linings and finishes. It has an implication on many elements and systems associated with the house. So bearing that in mind, that's the definition that I've worked with when we're talking about slab construction specifically. I'll also touch base on retaining as well. So I feel like those two are linked. Oftentimes, slab and retaining are part and parcel in order to make a property work. So it's quite key to get those two pieces organized together. This is the climate that we have here. So as you can imagine, cold is quite important, and there's a lot of emphasis and focus on that and what that means for the built environment. This was just a random day. Negative 10 degrees basically on the outside cladding. So you get an idea that we're pretty focused on how efficient we can be with how we assemble elements of the building, and especially focused on ensuring that the things that we build today will have longevity into the future. So this is a thermal imaging camera image taken of the outside of a structure. You can see that we've sort of dialed it up so you can begin to get where the difference in temperature is. And purple being the coldest, red, yellow sort of being warmer and hotter temperatures. But to give you an idea, you can see the face of the person in the center window there is actually red, and they're about 8 or 9 meters away from the glass. So that shows you that we had to get a lot of the imaging tuned up in order to see the differential. So this is an insulated slab edge. You can tell that there's really no temperature difference between the slab at the base here and the cladding, the wall cladding. So that gives you an idea of the benefits of a well insulated and well thermally broken slab. This is a same night at the time what was code construction, so a non-insulated slab. There's no underfloor heating. But again, you can see where that cold sits on that outside edge and certainly at the door itself. So that's just a traditional cedar door as opposed to a door that was built to take the environment. But you can see where that slab edge transitioned to wall, how much cold is leaking through straight through the bottom plate into the room. So that temperature difference from memory, that was 4 degrees there. And the red and oranges that you're seeing are just surface temperatures. The room was heated up to 20 degrees and then it was shut off. And so the slab temperature in the center of the room is 12 degrees. So that's the difference between 4 on the outside, 12 on the inside. So it's all still a relatively cold assembly. I did this purely as an experiment, and in retrospect, I probably shouldn't have. And I've got a project that highlights some of the benefits of not doing things like this. So I'll just transition to another set of images. I'll start here. So this is a very traditional slab on grade. We've used Max Raft in this particular assembly. What we've done here is that we've also insulated the garage floor. And the main reason for that was because we wanted to ensure that in the future, should the building be used for other purposes, partially for habitation, a sleep out, anything else, that it would be suitable for that in the long term. The other benefit that we found is that while there is a cost to insulating this slab, what you get in exchange for that cost is a dramatic uplift in utilization. So we've been building in Queenstown now for just over 10 years. And in that time, we've transitioned from building garages without an insulated slab to building garages with an insulated slab to building garages with underfloor heating and an insulated slab. So you'll see here that by insulating this slab, we've automatically guaranteed that you'll be able to manage the environment in there. This garage is fully insulated and fully lined when it was completed. And the other thing that we've done, because we're trying to manage the temperature between the two buildings, so in this instance, the slab is not heated. We've used simply air cooling through the form of a heat pump. So that heat pump system is what's providing the temperature regulation within the building. And this is a certified low energy passive house. So it demanded that we used XPS insulation for the perimeter slab insulation. And that's also why you will see that that perimeter slab insulation there, why we have XPS running through the thermal break between the garage and the house. So it's quite important, I feel, that you make sure that whatever your core principle or your basic principle about how you're assembling these things holds true, that you carry that through all the way through to all of your transitions and junctions as well. So even though the garage is insulated, we realize that these two environments will be used differently. And so we wanted to retain the ability to control the living environment to the same standard everywhere and not have any degradation in performance at that transition between the garage and the slab. The other thing that's really interesting is, and I'll show you in another project, but we have these footings that attach to the building, and this was to allow for wing walls to go out. So that footing there is connected through the use of fiberglass Martine bars. And that was to minimize the amount of thermal bridging that was going to occur. So our XPS insulation goes all the way around, and then our Martine bars go through. Because we can't access this particular stud bay after construction, once we've stood the other wall up, that gets insulated at the same time, which ensures that tangential cold bridging that occurs at this particular junction in the slab to framing detail is appropriately addressed and doesn't become a significant drain on the thermal efficiency of the project. This foundation detail isn't unusual, but it is something where we have found that when we take a look at the thermal modeling, that is essentially by going to a fiberglass bar here, it has quite a dramatic improvement in the performance of the main slab, even though this looks like quite a small fin sticking out. because of where it's located on the building, it would have made the difference. It was quite a significant difference to what we would have seen otherwise had we left a traditional steel bar going all the way through. The other thing that happens with this project is that all garages require some sort of a structural edge coming in. And what we've found, generally speaking, and we've tested this both in slab-on grades with underfloor heating and those without, is that once you insulate this wall and you have an insulated garage door, that thermal bridge that occurs at the garage isn't dramatically detrimental to the performance of the building as a whole. So again, we're not talking about the fine details that you would be chasing in full passive house performance, where this would be a horrific outcome. We're talking about things where you already have embodied energy being brought into it. So you've got some sort of energy going into the building already. This is a relatively small energy impact. There is a better way to do this detail using, come on, Dennis, using glass, essentially. But it is a more challenging detail to get right. But that's what we'd be doing in a passive house. We would have a full thermal breakthrough here, and then we would use often a polymer essentially junction to transition over that gap that we created in the insulation. So although the insulation is capable of taking load bearing, if we're using foam glass, it is a bit brittle, so we put a protecting element over that. But in the absence of pursuing passive house, this was a detail that we used traditionally. The reason I raised this particular building is because you'll note that it has a steel frame inside all the way through the building. So it starts at the front face. There's steel here, which we've set back to the inside line of the framing, and this is all ends up ultimately being filled with XPS insulation. Bringing your steel frames inside your wall is absolutely critical to getting your slab performance to work appropriately. So there was a time when there was a bit of debate around what you should be or how thermal breaks should be conducted. And when I say debate, it wasn't really a debate within the passive house community, but it was a debate at large within the building community and design community as to what was the best methodology for creating thermal breaks. And there was a time where you would use something like a block foundation upstand. You would then use a timber board to be your thermal break, and then pour your slab up to the back side of it. And your steel would often, as you can see here, your steel would often sit inside this wall assembly completely. And so it would be exposed to the outside elements in full. So at the end, this steel is fully enclosed. Here, we're partially enclosed, and at the front, we've hidden it within the wall itself. But what ends up happening is at this particular junction, and I don't know if I can zoom in, I can see. Yeah. So at this junction here, between your steel, where your steel comes into contact with your slab, what we noted when we did some thermal imaging was that if you had a timber border anyways, so if you weren't using at a minimum a 50 mil EPS edge or thermal break, if you used timber, and in this instance that was a 25 mil thick timber, and you put steel over it, what ended up happening was that for the first approximately 400 mil into the house, even though there was underfloor heating at 200 mil off the edge of the thermal break, there was a difference of about 15 degrees in the slab temperature because it simply couldn't cope with the thermal break that was created by the steel. The second thing that was very obvious was that generally speaking, you were about 8 to 12 degrees cooler at your immediate wall junction heat point here. I don't know if you can see that cursor, but just where your wall joins the slab here. That temperature difference was caused by that thermal break being completely inefficient. So even though within a meter, our slab temperature were reading 28 degrees, we were often down to 18 to 20 at that slab edge. So that's the amount of heat that you're losing consistently, which means that the energy that's going into that building is remarkably higher than it should have been. And I highlight that particular project because it is one that was personally very frustrating. I had ended up in a scenario where I had been arguing with the designer about wanting to change the slab edge. They did not want to do it. I then went to the owner, had them basically across the line, and then they decided at the last minute to take the advice of the architect that was involved and go back to this detail. The architect retired within 3 months of commencement of the project. So in essence, the architect had retired within a couple of weeks of me standing frames. And yet forever now, that building is underperforming because of that slab edge detail was allowed to go through because someone felt that that was appropriate detailing to retain. So that's, my personal story and involvement was something we couldn't fix within a building that we were constructing. And the outcome of that, I've been able to test and see. And if you look at what their operating costs are, generally speaking, because we've built a couple of homes of a similar size, but with differing construction for the slab itself, their operating costs vary anywhere from 40 to 60% more in winter to just drive that underfloor heating, even though we're using all the other same systems. So the underfloor heating is still the same energy efficient system. It's just too much drain on that slab. So I really feel that for me, what you do with your slab construction is absolutely fundamental to how your building is going to perform long term. I can take a break, or is any questions? No? Yes, no? Chat. Was it meant to be a low energy building? Yes, so that particular project is being submitted, correct? So that certificate has not been issued yet, but we have been compliant. Our paperwork's all in, and it's just going through the review process for that particular project. So this, can you guys see these images now? Hopefully that works. There you go. So this was a project that we had that essentially required us to have, because of the soil conditions that were present, we needed to have from memory, I think it was 450 or 500 high foundation element to it. And we needed to create this perimeter foundation. And there is also a central beam, which you'll see later, that all needed to be within the insulated envelope. And at the back of the wall where we have the blue XPS, you can see that there's a double layer of XPS. And the reason for that was so it would line up with our Nudura retaining wall. So the goal of this project was to do the best we could to insulate the slab from some relatively poor soil bearing conditions, which required a different approach where a max raft slab wasn't capable of providing the overall resilience that was needed for the loads that were going to be imposed by the renovation that was going above. So we have a central beam that runs through this project. We have 50 mil XPS around the outside. Actually, I think we ended up going with 60 mil XPS everywhere. And then at the back, we added an additional layer for the polyblock integration so we could have as much insulating at the back. The existing house is where you can see the plans in the left corner of the house, and they slope down to the retaining side as well. We also thought it was really important, even though the soils were fairly well draining, this slab is located at the bottom of a section. It's about 4 meters, 5 meters below, well, it's probably closer to 5 and change below street level. And so we thought that the potential for hydraulic pressure on the slab was relatively high. So we went with a better quality slab underlay. And we used, in this particular instance, we used Proclim as sill tape to seal all the joints. We felt that between the overlap and then the wide sill tape, we were going to get the best outcome. Under the polyblock portion where the foundation rotates up, we attached a sheet waterproofing to go through there as well. And the reason the waterproofing is quite critical, obviously, is that your performance of your EPS drops dramatically if it gets water in it. So we want to make sure that our EPS stays dry throughout the life of the building. XPS is a bit more resistant to, obviously, water coming in, but EPS is not, and it can dramatically affect its long-term performance. So at our window rebates, we embed timber in at the concrete pour stage, and then the the form that we've put in to create the rebate within the concrete is removed, and our H3.2 timber becomes embedded in. While it has a lower R value than the insulation, we feel that's a good compromise to get the bearing that we need onto it, to be able to fix all the pieces that we want underneath the window at the same time. Here in the top left corner, you can see the fiberglass Martine bars. So you can, again, these were put in for vertical alignment between the external foundation and the house foot foundation, essentially. So those Martine bars, again, have been really useful and quite impactful on making the house perform well. We then had 200 mil of EPS was used here to create the insulating layer under the slab. And then we obviously came in, and as you can tell, probably not so much, but this particular property is completely landlocked. So everything had to come in from other places. So our crane is a whole house away, sitting in a parking lot, coming over to pour the slab. So with the slab in, we've got all the starter bars in place for the Nudura to go in. And the other thing that we're trying to achieve here when we're talking about the lock-in effect is that we wanted to have a good slab edge insulation. And we also wanted to be able to provide adequate insulation to the retaining itself. So it was originally drawn as a masonry block wall. But in this instance, given site access, there was more than one benefit to using Nudura or polyblock. So in this scenario, if we had to take conventional block downstairs and mix mortar on site and then get them in place, it would have been walking up down flights of stairs, very little access. There's only parking for 2 vehicles on site. It's immediately on the road reserve, so there's just no space. So by doing polyblock, we could literally carry all the block down that we needed. It took us, I think, 12 minutes to get all the block downstairs. All the steel was easy to carry and put in place, so it made a big difference to the efficacy of actually installing a retaining system here. Again, that's what the Martine bars ended up tying into, if you're wondering why they were in space later. And then, again, that's just our steel getting set. We then come through, you can see our retaining wall structure is now in place. And I typically would like to enhance the benefits of the polyblock by going to a larger insulation value than the polyblock itself provides. So once we have the waterproofing in place, that's what's been done at the bottom. So that sheet then gets lapped over the top to protect it from any environmental degradation from water intrusion. Once that's in place, we then put in, you can see here in the bottom right, we added another 100 mil of, that was 200 mil of EPS. And that will run all the way up the block wall. So in this instance, we just did it long enough so we could put in the retaining and get in the drainage gravel behind it. And you can see the plastic there to help guide water away from it. But that 200 mil of EPS on the outside is a very cheap way of dramatically enhancing the performance of your wall. It fits in easily, it's light and easy to carry, and you get a much better outcome from it in my mind. And you can see kind of how it sits here with, this is the full assembly with the drainage pocket being covered, as well as the 200 mil of EPS that's in there while we created the rest of the foundations behind the property. The next project that I can share with you, and I guess one of the reasons that we really liked using or considering how we're putting our foundations together is this one. So this is quite different. So this project was a sloping site. We needed to try to come up with a way of not having to do a massive slab and foundation. The client wanted to stay away from concrete as much as they could. So everything in this particular project was done with timber framing for the most part. But the reason I raise this is that those foundations that you can see there are about 3 meters deep. The note that I forgot to make about the polyblock is that, and it came true with these foundations as well, as if you want to try to use low carbon concrete, polyblock is a fantastic way to do it. So what happens is when you're curing concrete, if you can control the environment and the water content effectively, then you get a better cure strength for the same value of the mix design that was presented. So the best example I can give you is that we had a 30 MPa mix designed for a 5-meter wall, concrete wall in polyblock. And we finished at the end of 45 days, we were at 68 MPa. And that primarily was the benefit of it being encased in polystyrene the whole time. So it wasn't drying out too quickly. It was able to, the chemical reaction was very uniform in temperature. It wasn't getting adversely impacted by the environment or having to play at the whim of what the environment was doing. And so we ended up with a much better cure time. So since that point, we have typically dropped our cement content, and then we've added, obviously, admixtures to that to try and reduce our overall cement content and reduce the carbon footprint of the concrete we're using. So in this scenario, we had the same thing. So we were able to use a lower value cement mix by design, so that when we got to the ultimate cure strength, we had achieved the outcome that was required by the engineer. So these foundations were, some of them were 3.5 meters deep, and they were scattered throughout the site. And the reason I have this particular example in here is that there was still ended up being ultimately quite a bit of concrete into the project. So being able to use that low carbon alternative was important. I sort of believe that fundamentally, if you're coming into a project, so you can see here we've got the piles going in, and this gives you a sense of scale of height, right? So those are water tanks that are completely underneath the property. If you're looking to do, if your focus is on, for example, reducing carbon, one of the key things that you need to also do concurrently with that is make all the right choices around things that are high carbon value in the first instance. So again, concrete, by reducing your cement, makes a big difference. But the second thing is you want to reduce, obviously, the operational carbon that the house requires in order to function. So you want to reduce its electricity usage, you want to reduce its energy reliance, and you want to make it as efficient as possible. So this house goes a long way to doing that. And we utilized, we got rid of steel everywhere we could. We have some stainless steel brackets, but there was originally structural steel in the building in a few locations. We were able to get rid of all the structural steel and go with glue laminated beams for all the floor support and what have you. And I don't have photos of it in this particular presentation, but what ended up happening was that we were able to use PIR, spray-on PIR insulation underneath the home, which gave us an incredibly high R value. I don't want to misquote it, but it was over an R4, and obviously helped to further make the supporting foundation airtight. We had with the benefit we had from that was that we've ended up with a home that so that's 130 square meters. I think it's about 140 square meters of living between the ground floor and the mezzanine areas. And they heat the whole thing with a wall panel heater. And so if you're focused on carbon, a great way to reduce carbon is to do just that. It's to remove the cement and greatly reduce your obligation to rely on energy to heat the house. So yes, the question was been raised. Dennis, are you part of early discussions, e.g. informing the engineering design, polyblock and Nadura, or are these variations you suggest during the project? So I've found that by and large, you're much better off to be able to influence the project at the beginning. We're fortunate in that we are typically engaged either concurrently with the design team, or we engage the design team on behalf of the owner. And so we're able to provide advice from the outset around products and methodologies and typologies that we want to be utilized within the project. For the project, the 3 projects I've shown you, only one of them were we involved in from the beginning, and that was the certified low energy home. The other 2, we came on board either at the conclusion, so when the consent was issued, and so we changed to the Nadura wall after consent had been issued. We did that as a minor variation. Or we were a part of it when the design had been set, but we had the opportunity to still influence the engineering and get some of the engineering redone to accommodate the changes that we thought were important and that were valuable to the owner, such as taking steel out of the building. I think and if that's a challenge that you're having as well, I mean, one of the things that we have found to be very valuable is to talk about, long term, what you're doing to the building and what choices you're making, how they impact your utilization of the project, and also your sense of home while you live in it. And so choices that go beyond just foundations, what we're speaking out most today, are very far reaching. So we have that conversation around triple glazed windows, for example, which are often come at a cost premium, but they have a dramatic influence, not just on energy efficiency, but more so, I think, even on quality of life inside, and just how quiet and serene it is when you're inside that home because of the sound absorbing benefits of that triple glazing. Let's see, what else do I have lined up to show you? So this is a project where I probably don't have all the photos here that I'd like to show you at the moment, but I can give you a sense of where it's at. So this was a renovation project. This was sort of a glass enclosure that was at the front of the building. You can see that from the inside of the building. This was a early 80s home. There was lino on a concrete floor down here. And when we stripped the building back, we had exposed concrete retaining. This is the original slab here. Just beyond working dog, we cut into the foundation that was there to create a sleeping space. But you can tell, and you could see from the way the building had performed, that all of this exposed concrete that had been put in had made the home incredibly cold. I'd been in it quite a bit. This is all single glazing. That was the only photo I've got in here, but this was all single glazing everywhere throughout the house. And it was an incredibly cold, very, very challenging building to heat. The windows were closed, all the blinds were drawn, the fire was going, and it was still cold throughout. And so the choices that were made back in the day as to how to construct this have forever impacted the occupants. And it's something that I think we need to fix when we touch a building. So in this scenario here, as I said, the area that the lower section just past working dog is where we poured a new concrete slab. This is what the building looked like as we were going through and doing the demo. So that block wall that you can see here, we talked about a thermal break earlier. That is the antithesis of a thermal break. This is just taking all that lovely cold environment from the garage and bringing it straight into the house. This retaining wall that you see here was the same. It went straight into the property, right into the stairwell over here. And all of that was just directly a part of the house. So we chipped the rock back a bit further, added polyblock again to the top of the wall to bring it up so we could get retaining off the back of the wall linings. And this gives you a better shot of what we did to try to improve the retaining there, because the dirt was basically overloading the top of it. So we knew the building quality was going to continue to degrade over time, and any renovation we did would suffer from the same thing. So we needed to improve that. We came through and redid the steps, and at the same time we used 50 mil PIR everywhere. You can see it underneath the concrete steps. You can see where our Nadura integrates over here. This eventually all became covered in PIR as well. We framed over the back retaining that we saw earlier and fully insulated that. So this is again a progress shot where every upstand we've gone through and insulated, and then we ended up putting fibrous insulation in front of this as well. So all of this is fully insulated further. And the amazing thing was, as soon as we put down the 50 mil of PIR on the floor, which you can just see sticking through the edges here, and the OSB on top, it had such an immediate impact on the quality of the internal environment. And you don't often get to see the benefits of what you're thinking of doing if you're building new. You only see the outcome, so you don't get to see what it could have been if you hadn't made those choices. You start from that finished position. So one of the nice things about renovations is that every time we go into the one, there's different constraints. In this particular one, we had the opportunity, we had enough room to add what amounted to be almost 70 mil to the floor. We had space to do that without having to disrupt what was going on, because we had gone through and changed door heights and everything else. So that meant that we could put this down, and it dramatically improved the temperature in that room. I mean, I think I wouldn't be exaggerating to say the temperature over the course of probably a month from when we put it in stabilized at about 5 to 7 degrees more. And that's with us just using it as a construction site, higher than what it had been without it. And as a finished room now, it's one of the nicest places. It's cool in summer, it's warm in winter. It's a fantastic spot to be. Whereas previously it had been wet and damp and just unpleasant all the time. So that gives you an idea of kind of what it looked like as we went through. Everything got waterproofed and sealed. Floor needed to be leveled before we could put the subfloor in. You could see all the insulation we utilized still to go in. But by waterproofing that as well, which is why I talked about the damp course earlier, that took a lot, I think, of just inherent moisture that was being brought into that space that eliminated that as well, which I thought was more influential than I would have typically attributed it to. Oftentimes when we go into renovation, we're not able to have as much space to affect all this change that we did here. And what we found is that while we think it would be much better to use a product like Marmox as an overlay to improve the R value of the slab, even doing something as simple as direct fixing, so by gluing and using concrete anchors, 12 mil sheets of H3.2 ply, we've been able to affect a really dramatic change in the sense of comfort. And I think that's something important to note. I've got another group of slides I'll try to open up. It'll just take me a minute or two to get it organized. But this is essentially an above slab insulation. And so even though this R value is less than what we would have if we were using, let's say, a max raft, it's still highly efficient and highly effective above the slab. There's a few different ways to do above slab installations. In the passive house that we did, we direct fixed 100 mil PIR from memory. We glued that to the ground directly, and that worked out beautifully. On another project, we did 70 mil of XPS, and then we put in a 50 mil topping slab with underfloor heating elements in it, and that worked out really well also. And as I said, we've done 12 mil ply as a thermal break, which has worked out well. But this has been a phenomenal outcome. It made the house quieter, and it dramatically improved the performance of it overall as well. Do you have to when do you choose to use PIR versus XPS? That's a good question. So there's sort of three things that come into play when you're trying to decide which insulation to use in my mind. So it basically goes down to how much space do we have. So if we have a lot of volume, the most cost-effective insulation is EPS. And if we know that we can keep it dry, then EPS is a great product. And you can buy a carbon-infused EPS that once you get to about I think the last time we did it, we must have used about 180 mil of it. It was performing very well when we then used fibrous insulation within the ceiling void. And the choice between using EPS or XPS for the slightly better R value was outweighed by the cost difference. I think for that particular job, the cost difference between using EPS and XPS for that ceiling void was something like 6.5 grand. And it just didn't warrant it for what amounted to about half an R value by the time we had finished the way that we had put our assembly together. So we were able to jig a few things around, and that became a really good solution. XPS I typically go to where I have less space, I don't have the funds for PIR, and I want to get a slightly better outcome, or I know that the insulation that I'm using, the XPS I'm using, may be subject to either airborne moisture or some other environmental impact. XPS is incredibly happy to be in some pretty bad places, so I quite like utilizing it in that instance. I think the other thing to bear in mind if you're trying to choose between XPS and EPS is it is a horses for courses. EPS, as I said, does tend to take on water, so you need to be mindful that you can always keep it dry. And the EPS does come, as I said, in carbon infused, which makes a difference again in the R value. Trying to choose between PIR and XPS is almost, there's two pieces to it. So XPS is sort of the only solution when you're trying to use it in a foundation where it's going to be weight bearing. Your grade 300, I think it's 300, 350, and 400 from memory is what we've used before based on the design. And that's pretty much the only thing that we've typically utilized underneath the foundation for load bearing is XPS because it has pretty good compressive strength. PIR I tend to use anytime that I'm doing a deep retrofit or something along those lines. So if we're renovating a house and it has 90 mil framing, I will use PIR because I want to get every ounce of insulating value that I can out of that wall. And we have to pay incredible attention to and care to the installation of it because the edge fitment is so important to retaining the value of that. PIR I tend to use universally on roofs, so that tends to almost be a roof solution if I'm putting a membrane roof over top of it. I also typically use it, as I said, for any retrofit where we're retaining 90 mil frames. And I also use PIR anytime that we have space as an issue, but I need to get the most out of my R value. So I will use, so we did an installation recently where we had some ducting that had to go into a cantilevered portion of the second floor. And that ductwork took up more volume than I wanted it to within the joist space. And so we had enough room to put in 50 mil PIR and still have our Safite linings tie through that area and adjoin other parts of the house. So PIR for me is when the budget allows for it and space is at a premium, that's a sure time to use it. As a rule of thumb, if I'm just trying to get as much insulation as I can, PIR is my first choice. And then EPS and XPS are typically more about what's functionally going to perform better in the environment that it's being put in. And there is a bit of a debate that I drill into to decide whether that cost benefit relationship is there. So hopefully that answers your question. Suppose the existing slab and foundations have been retained to minimize, oh, I guess he's saying, I suppose the existing slab and foundation has been retained to minimize use of new concrete. Did you have to retrofit or upgrade any waterproofing? Did the existing slab have damp proofing already? So we basically, for me anyways, when we do a renovation, we're trying to be very frugal oftentimes. And when I say frugal, renovations can get carried away on their own. So we try to keep as much of the footprint as we can. And if we can reuse the existing products, we do that. For that particular project, all the walls and floor framing were all remu. All of that got milled and it got used as internal lining for another project of ours. All the aluminum was recycled. The glass we used as base in a driveway. The tin was recycled from the roof. The ply was contaminated, was full of mold, so we couldn't reuse that. The block work, we used it for rough base for a drainage field that we had on another job. So we try to reuse or as much as we can to divert from landfill. But that was primarily the goal was to try to use what was there. The other problem we had with that site is it was all dug into rock. And so if we tried to go back outside and sort of interrogate and rebuild how that retaining was done, we felt we were probably opening up more problems than it was worth. So what we did in terms of waterproofing was we did three things. So we went to the outside, we dug down the outside and put polystyrene in a drainage mat against the outside wall and then filled that back up with drainage gravel all the way through. So there was pretty much free draining down that whole side of the house. On the inside, we used a product called Zypex, which was a penetrating waterproofing. And so we used that to waterproof the inside of the wall. And then we did that very early in the project so we could see it through a season and see if there was any leaks that came through. And then when we put the insulation in, we stepped the wall away so there'd always be a drainage space. And then we had a waterproof channel that went through there. For the floor slab, we didn't address anything. As I said, it was all rock. And the area in the garage that you might have seen at the beginning, everything underneath there was bone dry. There was no moisture in there or anything like that. So on that basis, we felt it was probably relatively reasonable that we weren't dealing with any water that was permeating through the rock. So what we did is we applied a topical waterproofing to the whole of the slab. And we did that over a screed. So we put a screed down to float the floor out because it was out of level by 40 mil, and then did a waterproofing over all of that. So that damp proofing was quite key to kind of getting everything to work right. So we damp proofed. Yeah, sorry, I got that backwards. We damp proofed, then we screeded, then we adhered our XPS to the our PIR to the screed. So that's how that process went through. The last project I'll try to pull up was external insulation on the outside of the 90 mil frame an option? So, how do I feel about 90 mil frame and external insulation? We have looked at it for a number of projects. We've done it on a brand new project where we had a 50 mil edge insulation on the slab. And then we went right to a 90 mil poly on the outside, which had a formed edge. So we overlapped by 50 mil and had a 40 mil lip that went down. So it was a really lovely drainage cavity, basically, with a capillary break in between. And so that setup worked really well in a new home. And the reason we did that was the clients, we looked at the difference between more slab for a 140 frame versus the wall area that they wanted, the room area they wanted to get out of their house, and they had a relatively compact footprint they wanted to stay within. So by putting outsulation on, it actually gave us more footprint inside. I think it was, I can't remember exactly, but it was surprising how many square meters we picked up by sticking with a 90 mil frame. And in that scenario, we did some Wolfley modeling to make sure we were okay, but we had XPS on the outside, we had fiberglass on the inside, and we used an Intello barrier just as kind of we didn't do it as a fully airtight house. The client didn't want to go that route, but we did it as kind of a best practice idea that we put that membrane in there. For doing a retrofit to an existing building, we feel that at the moment, you've got to be pretty passionate about it if you want to do it. So that means that you're definitely going in for a full reclad. You're typically going to have to redo all your windows. You're going to have to redo the way your waterproofing ties into your windows and so forth as well. So it's kind of like committing to the whole project in that way. And we've priced a project recently where it was actually more cost effective for us to do an external frame that we basically added on to the building to get to our wall thickness that we wanted for insulation than it was to put what at the time was recommended, which was PIR around the whole of the envelope. And I think those are, unfortunate choices that are very realistic, that you're often trying to choose between best possible performance outcome and financial constraint or financial capacity to deliver to that best performance outcome. And in this scenario, if we're talking about a house that's a few hundred square meters and you're talking about maybe a total heating energy change of maybe having going from, let's say, 8 kilowatts for that house to 10 kilowatts for the house, oftentimes you've already got some sort of heating that you're needing. And so as long as you're not pushing the boundaries on that, you're usually not increasing the cost that much. The example I'll give you in sort of a sideways note about that cost impact of heating is that I think I mentioned earlier that we started off by doing uninsulated slabs, then insulated slabs, and insulated slabs with underfloor heating. And what we found is most of our clients run their garage at about 16 or 18 degrees. So given that the garage will normally sit around 12 on its own, you're only raising the temperature 4 degrees. So the cost to idle your garage at that 4-degree improvement in temperature is incredibly low. So the cost to actually increase the temperature of the garage and make it a place that you utilize more is very low. So I think that's kind of another piece of that cost benefit relationship, is that unfortunately, slabs that we've done that we haven't put underfloor heating in, we can never go back and fix. And we've done an interview of our clients and have found that those who have a heated garage spend just a vastly more time in their garage. Again, bearing in mind, I showed you the snow on the ground earlier. So we are in Queenstown, but I'd say your utilization of that space goes up probably by 100 to 200% by heating it. So it's something that we will carry on, because we think that loss of opportunity, that loss of utilization isn't justifiable given the low operating costs. The ongoing cost is very, very low. And the installation costs are also very low. So if you've already made the step to insulate it, then the next two pieces are cheap. Your plant and equipment's already there. So to give you an idea, most of the plant that we use comes in 4, I'm pretty sure I'm right on saying this, 4, 6, 8, and goes up to 16 kilowatts are the heat pumps. And so usually we're not making a heat pump change. We're not having to go from a 4 kilowatt heat pump to a 16 kilowatt heat pump to kind of get the energy into the house. They're very small changes, and they don't sort of cost or have a dramatic impact on what the ownership is seeing in terms of their cost of running their property. The other project, this is probably a really interesting project just in terms of showcasing to you what a whole bunch of junctions of lots of different things coming together starts to look like. And the reason I raise it is that this was the same idea for this project. So you're looking into the garage from this space. So there's a garage. On the other side of the garage, you can see a wall in the distance. That's the mechanical room that's underneath a mid-floor. And just to the left of that is the main entrance of the house. So this is fully insulated, as you can see, all the way through. This is a polyblock retaining as well here, but this is what's called a 1 series. So same supplier, Nadura, but in this instance, the insulation is just on the outside. This is clipped to apply face on the inside. And then as we did on the other project that was down in the hole, this is all insulated on the outside by another 150 mil of XPS. So there's over 200 mil of XPS on the outside face of this wall, and this wall is 4.8 meters high, 4.85 meters high. So what we have here is you'll see that the underfloor heating tubing is still run at the same intervals, even though down here on the lower right, on the right side of those double green lines, that's the bathroom. On the other side of the thermal break here is the garage space hallway. And then to the left of the green line and all that timber is a sleeping area. So this is just basically a sleep out on the other side of the garage from the main house. This setup here is so that you can run these two places at different temperatures without adversely affecting the running costs and the operating costs of the space. So to me, this would amount to basically $1,500 of underfloor heating tubing, perhaps at the high end. And it's done a fantastic job of keeping everything together. I guess for me, these are those costs that I just think you do at the outset, and then you have all of this functionality and flexibility with the house in perpetuity. So to me, this is a no-brainer to kind of deliver to this. Yeah. So Simon, that's probably most of what I have to say in terms of that topic. I've got some more images and so forth as well, but they're not as organized. So don't know if you have anything you wanted to add or share at this point.
Thank you, Dennis. I know that I've learned a lot, so I'm sure everybody else has as well. Let's start off by just giving people a chance to ask some more questions about what Dennis has been talking about. So if anyone's got anything else they want to know, then look up your questions.
Let me see if I can share a video with you as well. One of the things that I talked about earlier was having an above slab insulation. Can you guys see that video?
Yep.
Yep, cool. So this particular project, you can see this is our internal timber framing, and you can see there's blocking that runs along the line here. Below that blocking is all EPS down to a bottom plate. And then we have 70 mil of XPS insulation here over a structural slab, and it butts into a polyblock ring beam or polyblock walls, depending where we are in the project. So this is a 50 mil self-leveling topping slab. So this is really what a very energy efficient topping slab looks like. So rather than having, let's say, a structural slab, some insulation, then another 80 to 100 mil slab, this is only 50 mil thick. And it's pumped out through a truck. I'll just turn the volume down on it because it doesn't make any interesting sounds. It's pumped out through a truck at the front, and you can just see how it's all pushed into the spaces and self-levels as it goes through. So that red pin that you can see there is the heights that we set everywhere. And so they just brought it up to that height throughout the floor area. And this installation, to give you an idea, this particular property is running quite a bit of solar. So I have to say that is true. It's got a 25 kilowatts of solar on the roof. But there's the polyblock wall on the left here, and that same thing, that polyblock wall is still below as well. So this house is 820 square meters. It has the garage is fully heated. It has, as I said, 25 kilowatts of solar, but its electrical run during winter, in the middle of winter, it costs $600 a month to run that house full occupied. So that's people living in it, having showers, heating the house, and living. So the solar does have an impact on that bill. I can't walk away from that. But at that size of a home, doing things like this make a tremendous difference to keeping things like your underfloor heating system working highly efficiently. So the other question was asked about insulation. This particular project was actually one of the first test cases for us in terms of trying to decide what insulation is right. And so what I mean by that is um, we were in the design process. We were asked about we were trying to get the budget down, sorry. There was 200 mil of insulation underneath the structural slab from memory. And we were trying to see how far we could reduce that. And we went and did a bunch of math with some much smarter people. So when I say we did a bunch of math, I called a guy and he did it for me. But what we found out, which was incredibly interesting, was that your underslab R value relative to your insulation very quickly hits a point where there's not enough gain to justify the increase in performance that you're getting. So although your R value might be skyrocketing up as you add more insulation under the slab, at some point that relationship of extra insulation, extra performance starts getting out of whack. So initially, your sort of insulation and performance are sort of more or less, I'm going to say, lockstep. And then suddenly, as your insulation increases, your performance gains get smaller and smaller relative to that gain. So this project was a great example. We saved 80K in insulation alone by reviewing that math equation to decide that it worked. And we found similar things have happened. I know this is outside of keeping, but just on this theme, we found some of the things are worthwhile investigating as well. So that renovation that I showed you where we had the block walls and the concrete slab, or the retaining wall and the concrete slab, when we, in the middle of modeling that, we were trying to work out why we weren't getting a lot of performance gains that we wanted by adjusting things. So we took all the windows out of the house from the top floor. And it made an incredibly small difference in the performance of the house. And the primary reason for that was that there was too much shading from where it was located on its site. And so that shading was basically mitigating any solar gain benefit that you might have seen that would have helped with, let's say, the overall heating requirement in winter. And so it's really important when you're going through this process, if you do decide to model your house, that you start poking and prodding at different pieces to make sure that the value that you think you are getting is actually going to be true when you finish the construction. So another example of that is we found that generically speaking, a 190 thick insulated wall, we'll call that a circa R5, R5.2 in insulation only. So the net R value is lower than that. But that 190 wall, in order for us to get an appreciable performance difference, and this is again assuming that anything outside of passive house, just isn't there. Once you get to 190, you're pretty much at a really good pace where any energy that you're putting into it is being utilized. So to give you an idea, our own house requires 5 kilowatts of heating is the maximum heating demand for it. If we'd increased our walls from 190 to 240, we would have required something like 4.8 kilowatts of heating. So there are much better areas to do it, which is why our roof is, for example, is R9 and change, because that was a better value spend. And sort of the same thing to think about when you're going through your underfloor and your slab construction is really pay attention to where your insulation is. Your edge protection is quite vital, getting that number right. And you may be surprised at where, for example, it's worthwhile doing something more on the shady side of the house to get that to work properly than it is in other areas. What was the overlay flooring on top of the screed? What was in this particular home, that was 19 mil timber flooring. So we have heat sensors underneath there. And as you're probably aware, timber flooring, one of the main reasons for that was that that screed cannot be polished and made into a finished floor. So you had to overlay it with something. Um, and so we used timber floor that was selected by the designer. That particular flooring surface was right at the limit of efficacy, because one of the things that you have is timber is obviously an insulator and you're trying to get the heat out. And at some point you can overheat the slab by having too thick of a timber over it, right? So that was at the limit of what it would do. But the interesting thing about it is that we don't feel a delay in the lag in the house performance. And one of the primary reasons for that is um, that the house doesn't have that much of a heat differential in it summer to winter. So if we have the heating basically turned off in winter, the house gets down typically to about 16 degrees. And in summer, it gets up to about 19 degrees. It occasionally goes over that, but that's kind of the range that that house tends to operate in. It's not perfect. That's with shades drawn and things like that. So as soon as you open all that up, the house will overheat in summer. But that's about how the house likes to behave. So that's where something like a timber floor works. If the house was less efficient, so the better example I can give you in terms of, when you're talking about locking in effects and what you want to do with your slab, we have a house that was in the same location, same orientation, and it was just one lot away from another property. The other property was 100 square meters larger, so that's relevant. But our house design, because of what we did with the slab and some of the ceiling insulation, was 8.5 kilowatts of heat energy. It had one heat pump that was wasn't fully engaged, and the other house had four. And our owner went to the other home, and this is something I didn't realize about a high performance house until later, but he went to the other home and he said, look, why is the underfloor heating? When I go to the other house, the floors are really warm underfoot. I love it. And my house, the floors are cool. And the reason is you don't need that temperature differential. You're not running your floor at 28 degrees. You're running your floor at 21 or 20, which is perceived as cold. So one of the key things to do when you're looking at putting your house together and assembling it is to test all of those pieces really strongly, and to get the right mechanical assistance in place if that's required. So if you're going for a passive house design, for example, you will find that you'll put insulation in places that you wouldn't normally do. So we put for a passive house that we did, we insulated under the foundation, put the foundation in, and then insulated on top of it. And the reason was that the foundation was such a large thermal mass that we had to create a break for it and try to bring it inside the house, whereas the slab itself could cope just with the insulation that was going on top of the slab. But that part was very important to get right for that particular house. And it was also interesting in that property where the block wall needed to be insulated on the outside, but we needed it on the inside in order to prevent overheating. So this idea that concrete or block walls are passive heating or they're passive cooling is not a rule of thumb at all. They have the capacity to work in either way. But if you're putting a foundation together and you have a huge amount of exposed slab and you've got it exposed to a lot of glass, there's a very good chance that house is going to overheat something awful and you can't manage it. Whereas you could have a similar design and provide shading and only have a limited amount of that slab in the sun and find that it works perfect in winter because it doesn't overheat in summer, but the sun comes in winter and warms it up and it maintains that temperature throughout the year. So that's one of the things that's really key to understand as well, is that your slab doesn't function as an inert thing. It does have an influence on the house, and you need to understand how it's going to function and what's going to happen. A question: in retrofitting your project, adding insulation over an existing uninsulated slab, what vapor barrier you use to reduce the risk of condensation? So that's a good question. I feel like there's a couple of ways to answer that question. And probably the simplest thing to do in the first instance is you can get a vapor barrier test kit. So you get a test kit, you seal it to the floor, and you can find out what sort of vapor pressure you have in that floor and in your slab. If you have an active problem, then you'll need to actually do some research to find out exactly how to address the problem that you have within your slab. For the floors that we've done, we don't have a hydrostatic head pressure problem. So what we typically use is just a relatively generic floor sealing compound like you'd use for any timber floor. And then we glue directly to that, which provides its own membrane to an extent. It's not perfect, but it does provide a level of a membrane. And then our H3.2 ply over top of that has an influence as well. So that's sort of a very generic answer to give you. But if you feel that you've got a hydrostatic pressure problem with your slab, then you need to review that specifically. But there are kits that you can buy to test it. Hydrostatic pressure under a slab, if it was a really significant problem, will require a very considered solution because you won't be able to address, let's say, the areas underneath your bottom plates and things like that. So most of the time, hydrostatic pressure just needs an area to vent. So you might be able to create a solution for that where you have a perimeter, let's say, around your insulation that allows any moisture to accumulate to come up and into the home in some capacity. But again, that's just very generic feedback from dealing with floors of different types. It isn't going to be specifically useful to your project, but it gives you some context as to what to look at and what to think about. How do you determine how much thermal mass you can leave exposed? Well, firstly, I think you need to make sure that the designer you're working with is switched on. One thing that will be very helpful is that if you use the PHPP software package, so the Passive House software package, it will give you an indication generally on how your house will perform. So it will show that, let's say that it's prone to overheating, and you might be able to look at the design and from the solar study that you've done, which shows the sun angles and light angles, that actually your slab is getting a lot of exposure. And by creating more shading, that it helps the house perform better. So that's kind of an easy way to test it in the first instance. What we tend to do is we do a sun shading model first to see where we're getting the sun at different seasons. In this part of the country, basically, if you have an eave that's 2.2 meters long and it's about 3.1 meters or lower, you're going to basically cut out all the shading from your windows as long as your windows aren't higher than 2.4 in height, right? There's a few assumptions there, but you get the idea. There's a line where it will cut out the sun. And yet in winter, when the azimuth changes dramatically in the sun, you'll get all that solar gain coming in. So your PHPP software will be useful in seeing to see if you get an overall increase in the performance of your home in terms of too much overheating if you have a lot of exposed slab and it's open to the glass. The second thing you can do, which we've started to use more depending on the project type, is there are providers in the market that can do active modeling. So what they do is the PHP software is focused on the envelope. And so it's focused on this entire house. We're going to treat it like it's one organism, and we're going to see how that house as a collective environment performs. And so it doesn't go down into the minutia to say that the bedroom at the south side of the house is 4 degrees cooler than the living room that's on the north side of the house, for example. But it will just look at how the house overarchingly is performing and tell you what it's doing. You can go and get and interrogate that information on a room by room basis actively, and then you can plot for the hottest day of the year, coldest day of the year, and it can tell you where the challenges are. So we did a house recently where we knew that the PHPP, although we were satisfied with the house's performance, we knew it wasn't actually telling us how the house would behave, because we knew we had a lot of south rooms and a lot of north rooms, and there was no way that this house was as happy as the software was telling us. And so we went into each of the rooms and did this active modeling and found that we had to shade two windows, which weren't very large, on the west in the master bedroom to drop the temperature in there. And we needed to create some active shading in the living environment. Because if you're looking at building a warm house, one of the things to bear in mind is you've made your slab really insulated. So it's not going to lose a lot of heat and it's not going to take in a lot of cold. So it's going to kind of just exist in whatever environment you give it. You've then created an envelope around it that's going to do more or less the same thing. So if you lock everything up in that environment, and even if, let's just say you don't have the ventilation system on, what happens is it gets a little solar gain and it might lose a bit over the night, and then it gets a little solar gain. But cumulatively, as it cycles over time, 7, 8, 10 days, that temperature just starts to rise if you're getting too much solar gain in the house. So that's something that I think really bears the attention being paid to, is looking at how your solar gain is going to affect things. And one of the key things that you can see is that if you've got a lot of exposed slab and a lot of glass, your slab temperatures are just never going to allow that dip. You'll actually find that the sun will go down, you'll get a rise in temperature, which seems extraordinary, but it's just you're getting a rise over time. Then you get a dip before sunrise, then you'll start getting a rise again later in the day, and that will carry on. So very important that you have a look at that. And as I said, the two tools that are most useful to get an indication of where you're going and whether you need to dig deeper are the PHPP software package and your your solar modeling to show just where the sunlight's coming in through your windows and so forth. Sorry, Simon, I think you're muted at the moment.
That's better. There's a question from David earlier when we were talking about outsulation, and he's asked, was that direct fixed to the frame? Now you're muted.
Yes, the intention was to direct fix it to the frame. Yes, yes, it was. So the basically I treat the outsulation as if it's inside the weatherproof envelope. So in my view, that's the best way to treat it. There are products that allow you to do it the other way around, where the insulation that you put on the outside of the building is essentially fully porous. So the rock wool just allows you to everything to just pour right through it. It doesn't take on water. It's not hydrophobic. It's not, I think it's hydrophobic, but anyways, it doesn't want to take on water. So you can do that as well. And you can put that on with a series of clips. I guess to date, we've done things as conventionally as we can, and we've looked at other systems and just haven't found one that's hit that sweet spot between owner engagement and cost, because everyone's trying to balance those pieces out, and we just haven't found that solution to work. In terms of solutions, I think the interest in external insulation is fully appropriate, and it works really well. We often get this question in relation to things like SIPs. Are SIPs better than standard wall framing? Is polyblock better than SIPs? And it's all very much a horses for courses thing that you need to get right for how you're putting your building together and how you're assembling your products. So SIPs for me, for example, I want a very simple structure with not a lot of corners. That's single story. To me, that's the perfect time for SIPs. And I want it to be not any wider that I don't have to do a lot of structural retrofitting to them to make them work as a roof structure. So that's how I use SIPs. Polyblock, I want the same thing. I want regular corners. I want relatively large volumes. I don't want a lot of wall changes. And I want it to be able to offer up some large spans so I can use concrete beams to suspend things. Once you get beyond those two pieces, I've found that economically in the market, there's very little differential between building frames on site and purchasing prefabricated frames and other systems. So where the benefit is often not in cost, it's in time. And that time is usually not terribly expensive in a residential project. There's not a lot of overhead holding costs. But for example, that other building we were talking to you about, I'll see if I can pull up a picture. I can just show you the benefit of polyblock on that particular building, where it allowed us to, because you need to see the structure and then you can see why we use polyblock. I mean, it just makes perfect sense once you see it. That building, we put the entire structure up in 3 weeks from this picture here. We were basically 3 weeks later. So I think a week after this, the slab went down. No, maybe the slab might have been a couple days away actually looking at this. And then 3 weeks later, all these walls were up, complete and poured and finished. And this is 610 square meters, this place here. We would have struggled to do that any other way that efficiently. And then a couple days after that, we put a prefabricated roof on. So, this is where you couldn't get a better house for polyblock. Could it be more square, right? It is absolutely perfect. It was all designed for polyblock. Everything worked well. This whole outside corner here is completely open. It's just glass in both directions. So we've got a big spanning concrete beam. There was some massive 10-meter window across the center here. That's a big concrete beam. So, it really was a horses for courses thing. And I think that's important when you're looking at different building materials and materiality, that it isn't that SIPs are the best. It isn't that wall framing is the best. And it isn't that polyblock's the best. It isn't that steel to steel framing I've got problems with, but it isn't that steel skeleton structures aren't functional either. It's just choosing what's best horses for courses solution for your project. How are polyblocks finished on the EPS side, both inside and outside? So each manufacturer of polyblocks does them differently. We've used all the polyblock that's available in New Zealand. We tend to use Nudura tends to be our go-to polyblock. And the reason for that is, and I'm not going to answer this question very well, is that it has a skin on the outside of it that makes it, that gives it its own weatherproofing element. So it doesn't require a building paper or anything over it. It's its own waterproofing agent. Once it's completed, it basically functions as a rad board. The EPSB that they use is proprietary, supposedly, and it's magic. But accepting that, and maybe with a little bit of skepticism around how magic it is, the one thing I like about their product is that it's highly, highly durable. It's very easy to move around, and I find that it functions really well. Again, it's horses for courses. It's about how much you're using, where you're using it, how it's being designed, the skill set that's available for the tradesmen that you're using in your area. All of those have an impact on product choices and selections that I think are relevant. I think one of the key things to bear in mind too is that you need to, when you're looking at your slab, just to kind of make sure that we stay to topic to some extent, is choose which XPS or EPS sort of is the right outside face for your project. My preference is always to use EPS, which is quite odd. But the reason I like EPS is it's the easiest to plaster over and put a waterproofing element on. And oftentimes I'm not scratching unless I'm doing a certified home that has very little or no energy being introduced to it. I don't necessarily need that small amount of performance benefit that XPS gives me. But XPS, you have to basically scratch the surface up before you can apply stuff to it. And it always makes me feel bad if I have to alter the way a finished product comes out because you're taking the skin off it to an extent. So my preference is to use things that as they come to the best of their ability. And EPS is very flexible, easy to use, and we like using it. But yeah, that's food for thought.
We've been talking a lot about concrete slabs and insulating them. You briefly mentioned some timber subfloors and insulating them, and I think you mentioned a spray-on product. Do you want to tell us some more about that?
Sure. So when we look at we don't do a lot of timber frame subfloors typically for new construction. It's not common. We've probably done two, I think. So it's not common to do, but both of the ones that we've done, we've both used spray foam insulation. So it's probably actually PUR
Mhm.
spray foam insulation. So that is essentially think of it as the same thing that comes out of your spray can. Basically, if you use a can of spray foam, it's the same idea, but it's just on an industrial basis. The other thing that it does is it allows you to go around all of your penetrations in the slab, I mean, in your subfloor, and it seals your subfloor and makes it airtight as well. Plus, it's not susceptible to wind wash. So that's where I was going with renovations. Renovations, oftentimes you don't have enough space to get in there with the plant and equipment and get that done. So we tend to use polyester insulation, and then we use a building paper, whatever cheap building paper we can find. We use building paper over it to get away from the wind wash because all of that fibrous insulation, the quality of that the insulation value of that comes from holding air within each of the fibers. So if you get wind across it, you reduce the R value. So we need to put something over it to stop the wind wash from going through and having an effect on it. That's the beauty of things like PUR, is that spray foam both acts as an airtight barrier. So it's fantastic for that. It seals all your penetrations. Plus, it's not susceptible to any damage from wind-related wind wash. So you keep that R value and retain it all the time, which is quite good. Continuing on with the previous question, what's the finish on the interior side if you use polyblocks with EPS face also on the interior side? Do you render over, line over, etc.? Well, we have finished our EPS in pretty much every way you can think of. So the block that we use has a spine in it, if you will. And so that spine allows us to fix product to it. So we have lined it with jib, we've lined it with plywood, we've lined it with finished flooring product and architectural timbers, and we have finished it with plaster, and we finished it with, come on, Dennis, with Italian skimmed render. I can't think of what it's called at the moment, but a beautifully flat finish. So you have a lot of flexibility in how you ultimately finish your polyblock wall. It's not limited to simply what's there. Probably the other thing to bear in mind if you're using polyblock is EPS tends to react with electrical cables. So all your cables need to be cut out and then put in a PVC pipe or something like that, or protected, and then run in the polyblock that way. And yes, plasterboard can be direct fixed to the polyblock. The key thing to that, Mateo, is that your installer needs to have his P's and Q's. He's got to be organized, his I's dotted, his T's crossed. So we've been using polyblock now for getting close to probably 8 years from the first project that we had with it. And as a result of refining the process with the installer that we've used, because we've consistently used the same installer if we don't do it ourselves, We have gotten to a point now where our walls are typically within about 3 mil out of plumb over 3 to 5 meters, depending on the height of the wall, and they're straight. That makes a massive difference. One of the first projects we did, the walls were really bad and we had to pack them out and we had to sand them down. And it just about made me decide I was never going to use polyblock again. But we decided there was probably an installation effort that we could make to make the install better, and true to form, everything's come right since then. And we've fallen in love with the product, and it's really good. But you've just got to get the installation right. It's very key to getting that straight and flat and finished. Venetian plaster. That was the other thing that we've put on the polyblock. I knew I'd remember the name.
So we're getting close to close off time. Thank you, Dennis. I've got one last thing. You've kind of mentioned that a number of your projects you've done some monitoring on. If that's correct, what systems have you got in place to monitor your projects?
Right. So very low tech. So we did a couple of things for monitoring. A few years ago, we put an ad in the paper and said to everyone, if you want a free digital thermometer, give us a call. And you just have to fill out this A4 sheet for us for, I think it was a week, and you get it for free. And it was checking all the temperatures, external cladding, window wall junctions, doors inside and out, joinery, glass, floor temperature, ceiling temperature. So it was those basic temperatures, and we wanted them done at different times of the day, etc. And so that gave us a baseline for building performance generically within the area. And we knew a little about every house. What was a code minimum, whether it was so old it didn't meet code, whether it was high performing or not. So that gave us that. And then for our own homes, that gave us a big background knowledge of just how houses perform in the area. We then, for our own homes, what we tend to do is we look through the data logs from the ventilation system and the underfloor heating to see how those are performed and the energy output that they're using. We then come in arbitrarily, basically, and we have given every customer has a digital thermometer. And of course, new people, new houses, they give a lot of data initially. So you get all this feedback and there are all these questions that come with it. And then we have gone out on our own and done that, but we also periodically go and get thermal imaging done so we can just see how the house performs over time. We want to see if anything's degrading, if we're getting any failures in seals, if we're seeing any window adjustments or movement, and whether the wall performance is increasing or degrading. And what we found historically on a curve is that by year 3, your house is performing much better than it ever did on your move-in day. And from year 3 onwards, it's pretty stable. And I know that's been backed up internationally as well, but it's interesting to see it on your own. So the data that we've collected has shown that pretty consistently that we know between building type, because we haven't done a large number of homes, but we've done enough that are within similar sizes, that we can tell you things about occupants' health. We can tell you basically how often the kids get sick, what it's costing them to take baths every week for 3 kids versus what it's taking a retired couple to live in their home, and the different temperatures that they're doing and how people use and adjust the temperature over time. So that's a very good reminder about lock-in effect. We started doing this, and this sounds terrible, but basically we had a series of customers that came through that were all older than 60, and they were all building essentially their retirement home, and they were looking at a couple of things that they wanted to do. And most of the time they were trying to under insulate and under illuminate their house, in my opinion. So they were trying to be really cost effective with their insulation and really cost effective with their lighting and electrical. So what we did was we sort of twisted their arm and we put in more insulation than we wanted, and we put in more lights than we wanted and dimmers. And what we found initially was people would come in and they were quite frustrated. The house was too bright, all this sort of stuff. Some of the people have been in their houses for 7 years. They've added lights. So they took hallway lights out, for example, they've put them back in. They've got dimmers all the way up, and they've continued to increase the temperature of their home that they use as a static temperature. So again, being New Zealand, people are very hardy in this country, and you have retired couple moved into their house and they wanted the temperature set to 18 degrees in winter, and they had the windows open in their bedroom all night. By year 3, their windows were closed and the temperature was still 18 degrees. By year 5, the windows were closed, the temperature was 20. And by year 7, it's 21, and their windows are closed all the time and their lights are on all the time. So all that has made a difference. So by using things that were always going to be energy efficient, there hasn't been a massive ratcheting of cost, because that differential of running the temperature up hasn't changed much, because the house is really efficient. So once it's reached its temperature, that big push to get the energy in is over, and then the management of it's very low. So that's why we're saying, that's why I guess what all these talks are about is that, get these right elements of the building put together at the beginning, because then there's nothing that you need to do later to help improve the quality of life or the performance of the home for the occupants of the home. We're really fundamentally very, very happy and convinced that someone will come in and they'll remodel the house. They'll put in different wall linings, or they'll paint the walls, or they'll change the kitchen, but they're never going to change the slab or the walls or the windows. Those are performing really well. They're never going to be a point of contention for the house. The outdoor heat pump might break down and need some work, but that's as bad as it's going to get. And for those in a passive house, obviously it's the same thing. The ventilation system might need replacing, but nothing else to the house is going to need to be done. So I think if you can take that approach, apply it to your budget, build a smaller house, get better for it. I mean, we've built, that one house we showed you is the biggest house we've done. It's 820 square meters. At the same time, we've done a house that's like 87 square meters, and they're both spaces. Basically, they're both built the same way. They have some differences in materiality, but the fundamental approach to why we built them the way we did is the same. And both people have the same experience. The little house, it's electricity bill in the middle of winter is something like $115, and they're in love with their house and they're warm. So, it makes a massive difference to people and quality of life, and it's a quiet environment. Is there much price difference between the polyblock suppliers? Yes, there is. So it's definitely worth doing your research, because the cost of polyblock isn't just simply the cost of the block and the steel, the installation factor, the quality of the outcome, the retrofitting, et cetera. So all of that's about finding a person. If you're looking at polyblock, find someone who likes the product. You can go see their homes. You can speak to someone who's seen it done before and really understand the pros and cons of what they're using. As I said, we use Nudura for a reason. We really like it, but we're not promoting them over anyone else. It's simply that that's a product that we've used that we found works for us. Other people will find products that work for them and their installer community.
Awesome. Thank you very much, Dennis. It has been so, so informative. Your knowledge is incredible. And also, once again, thank you for sponsoring this wee series of webinars. So yeah, we're 25 to 6. We've all learned a lot. So good night, everybody. Enjoy your evenings, and we hope to see you in the next webinars.
Thank you, Simon.
Thank you.